Lecture 24 covers section 7.2.2. At the end of today's lecture, you should be able to analyze trusses using the method of sections. Now, to employ the method of sections, we first have to construct a global free body diagram to determine the reactionary forces of our truss structure. This is the same as we did in the method of joints. For instance, if we revisit the truss structure from lecture 23, we can determine the reactionary forces RAY and RAX at pin A and RBY at a roller support. Then we will proceed to cut the truss to solve for our internal reactionary forces in each member. Now note, each cut represents an unknown, and we can only have 3 unknowns at a time, for we only have 3 equilibrium equations: the summation of forces in the x direction, the summation of forces in the y direction, and the sum of the moments about a point. Thus, we have to be very selective about our cuts. Additionally, when we make our cuts, we recall we express the internal reactionary forces of the members existing outward from the cut, i.e. they follow the unit normal. Our sign convention is opposite that of the method of joints. Now, let us reconsider the truss from lecture 23, example 1. We want to determine the forces existing within each member using the method of sections. For us to begin, we will construct a global free body diagram and then employ our equations. We will not spend time on this, for we've seen this global free body diagram before, but we'll refresh our values. RCX is equal to 0 newtons, REY is equal to 10,000 newtons, and RCY is equal to minus 7,000 newtons. Now, to begin, we will cut members AB and AD. We will draw our forces FAB and FAD acting away from the cut plane. Thus, we can apply our equilibrium equations. First, we'll take the summation of forces in the y direction. We'd have FAD times the sine of the angle between member AB and AD, which we found to be 8.00 meters per 10.00 meters, or a value of 0.800, plus our applied load of 2,000 newtons. We find FAD to be equal to minus 2,500 newtons. A negative sign indicates that our member is under compression. Now we can take the summation of forces in the x direction. We'd have FAB plus FAD times the cosine of our angle. Now, the cosine of our angle is simply 6.00 meters per 10.00 meters, or a value of 0.600. The summation of these two forces is set equal to 0, and we find FAB to be equal to minus FAD times 0.600, and this is equal to 1,500 newtons. A positive sign indicates our member is under tension. We'll proceed through our system and we'll cut members AB, BD, and DE. It is okay if we cut the same member twice. We cannot have more than 3 unknowns at a time. So, conceivably, we could cut 4 or 5 members if we knew 1 or 2 of the internal reactionary forces. Thus, to begin, we'll take the summation of forces in the y direction. We'd have FDB times sine of theta, which is 0.800, and this is equal to applied load of 2,000 newtons. Thus, we find FDB to be equal to 2,500 newtons. Then we can apply the summation of forces in the x direction. FDB times cosine of theta plus FAB plus FDE is equal to 0. Cosine of theta is equal to 0.600. Recall we just solved for FDB and we have FAB. Thus, FDE is equal to minus 3,000 newtons. Recall the negative sign indicates this member is under compression. Now we can move through and cut members BC, BE, and DE. Applying the summation of forces in the y direction, we'd have FBE times sine of theta, which is 0.800, plus 3,000 newtons. The sum of our applied loads is equal to 0. We find FBE to be equal to minus 3,750 newtons. With this value, we can apply the summation of forces in the x direction. We'd have FDE plus FBC plus FBE times cosine of theta, which is expressed as 0.600, and recalling that we just solved for FBE, and we have a value of FDE, we can solve FBC as 5,250 newtons. Now we can cut members BC and EC. In doing such, we recognize, once again, we only have 1 unknown. Thus, we can apply the summation of forces in the x direction. FBC plus FEC times cosine of theta is equal to 0. Or we find FEC to be minus 8,750 newtons. Note that we did not have 3 unknowns simultaneously during this process. Thus, we did not have to use the summation of moments equation. But if we did have 3 unknowns simultaneously, we could use our summation of moments to solve the problem. Now, comparing our results to the method of joints and recalling our sign convention, we can see each member, such as member FAD, FAB, FBD, FDE, FBC, FBE, and FEC, were solved to have the same numeric value as well as experiencing either the same tensive or compressive forces.